Okay, so we're recording, and so last time we did a demo on how to see Postgres pages and their tuple locations in the files, and we're going to do a recap of what we started in the last lecture. So we started with file storage, and then we discussed that how different database systems store their data in different file formats, and you cannot move one file format to the other. So like if you are transporting Postgres files, you cannot read it through MySQL. You'll have to, for data migration, you might have to convert that data back into SQL queries and then rewrite those SQL queries into Postgres format and then just execute them on the Postgres side. But you cannot just pick up raw MySQL files and put them in Postgres directories and expect it to work. So then we looked at something that Oracle did that they bypassed somehow the operating system read and write calls and embedded their own instructions in the Sun OS, I think, for their database to run faster on those machines. But then this died out quickly, I guess. And then we studied about Storage Manager, that how Storage Manager is aware of how to write pages, how to read pages, what kind of localities do we want, like how to order read and write so that you can maximize your caches and sequential reads and writes. Then we talked about what is a page. Page is a location, byte offset in a database file, which is of specific size. Like if I want page 2, then in the specific database file, I'll just say I want page 2, and this is the page size that this file is following. So I'll just multiply, like we saw here, that if a page, hold on, like if a page is 496 bytes, that's 4 kilobytes, and I want page 20, then I just multiplied that number and I jump to the offset in the database file, and I will get the page. And from that offset, I just need to read 496 bytes because a page is fixed size. And usually a page is fixed size. And we also talked that enterprise systems like Oracle and my MS SQL. Uh, I think this is a recording or not. Yep. Okay. We also discussed that how enterprise systems, Oracle and my MS SQL, they also allow you to define various page sizes for indexes for different tables, and these pages are read into memory into something known as a buffer pool. And given in the enterprise systems, you can also define different buffer pools that I want buffer pool of this size for this table, this size of this table, and so on. So that's what the money is for in databases, right? So then we discussed the concept of pages. There are notions of pages: hardware page, OS page, and database page. And we discussed what all of this is. I also mentioned that when I'm doing a move instruction from the CPU to a RAM address on the, like I'm doing a move instruction to a memory, like writing back to the main memory, then my OS actually writes 4 kilobytes pages. Now that statement was not true. That statement is, I made a mistake. You specifically write that particular address, like given that byte, you write those bytes, given that you're doing one byte operation, or maybe you're doing a move W, that's a move word, and your word size may be 4 bytes, or you're doing like a move L, that is move long, that is I think 8 bytes, depending on what instruction set you're using. And so yeah, you're writing that particular offset in the RAM, not the whole 4 kilobyte page. The page concept just arrives so that you can swap out pages. So when your system is under heavy load, you have opened bunch of applications, and you don't have enough physical memory. So what your operating system does is it takes out chunks of RAM and writes them out to the disk for the programs you're not using. And when that program comes back alive, like when you open the window or something, and the OS context switches, then it fetches those pages from the disk for you. So we discussed what database page sizes different databases follow, like 4 kilobytes is a common one. Then you have 8 kilobytes, and famously, like MySQL does 16 kilobytes by default. So these are default you get, but you can also change these. Like SQLite can go down to 512 bytes, I think. Yes. Andy said in one of his lectures that MySQL can go down to, like, sorry, SQLite can go down to 512 bytes per page. Then we discussed that how if you have a read-heavy workload, then you should keep your page sizes large. Why? Because in a larger page, you would get more data and you would just reduce the number of reads you're doing from the disk. While in a write-heavy workload, you should keep your page sizes usually small, uh, depending on what use cases you have. But the reasoning behind this is that when you have smaller page sizes, you are writing specific offsets in a page and you are writing a smaller block out to the disk. So imagine if you have 1 megabyte pages and you want to just edit 1 byte in that page. You need to read the whole 1 megabyte page. You write the 1 byte, and then you write back out the 1 megabyte page. Why? Because the SSDs and the disk is a block addressable memory. So you don't write out 1 byte at a time, you just write out a whole block and you write out the whole page because we're discussing this in the context of a database page. So whenever you are writing to a page, you need to write out that whole page to maintain consistency because that's what the database management system ensures that if you give me a page to write out, then I will, if I say that I've committed, then I will make sure that I see that particular page data when even if I crash. Then we saw that what kind of page orderings are there in the database file. So we discussed heap file organization. That is nothing. It is just unordered collection of tuples. So wherever you can find a space, you just push a tuple there. So Postgres does this, and so you have a database file, and when you are doing an insert query, then you just look at the free space map. We saw in the tutorial that what free space maps are, and you look at the free space map and see what pages are empty, and you push the tuple in the particular page. So there is no ordering to that, but you maintain higher level data structures like indexes or filters. Filters are just you usually maintain indexes to maintain some order to this data. So let's say when I'm doing a select query on the primary key, I don't go about sequentially scanning the whole page, the whole database file. But instead, what I do, Postgres build the default primary key index for me. Hold on. Yes. So Postgres builds a default primary key index for me, and I just look at that index and it points to the particular page and the offset in that page. And I just jump there and read the tuple out. We also saw that there is another thing called as a tree file organization. Uh, in what sense? We described it as some ordering to the data on the database file. So imagine you have a database file broken into a bunch of pages, and you are not randomly inserting tuples into those pages. You maintain some higher level logical order to that, and the storage manager is not the one doing that. The execution engine above the storage engine and the buffer pool that ensures that the logical ordering is maintained. So storage manager has no idea that it's writing to a B tree or it's writing to a hash table. It just reads raw bytes in and out of the system. Sorry. So it just reads raw bytes in and out of the system. So uh, the execution of engine above the storage manager ensures that you're maintaining some order to that particular data. So drew this tree structure where you're inserting data, and depending on the key, depending on what order you're following, you go to the left or go to the right. We also took this analogy of a binary search tree that if the value is less than the parent, then you go to the left, and if it is greater than 10, the parent, then you go to the right. So we also discussed that there are other file formats which are not widely used in the modern database system. This was a thing of the past, like in 1980s or 1990s when IBM was launching System R. I think this sequential sorted file organization was in System R. I'm not very sure about that information though, so you might want to recheck that. So, um, yes, so we discussed a bit about heap files that heap files are nothing but unordered collection of pages and tuples with tuples that are stored in random order. So you don't have order in the heap file. You maintain higher level indexes like some structure at a higher level like an index to look into the heap file. And the database needs additional information to track the location and free availability space. So we talked about these free space map files. We saw in that also the tutorial we did last time, yesterday, I think. Yes. So we saw that for every page, you get the location by page relation file path, and you look into that file, so you can see all your raw tuples. But you also see that there's another file called as it has an suffix of FSM, I think. That spells out for free space map. That maintains the free space amount of free space available in different pages of the database systems. I'm sorry if I'm rushing through. I have to get somewhere, and I just have half an hour to deliver this. So uh, we'll just try to complete pages and files, and we'll see how far we can get. So we discussed more about heap files. Then we talked about the page directory, that a directory is maintained which contains the metadata like the starting page of a table, then a starting page of an index, and this directory can contain various database objects like metadata of various database objects. Like index is a database object, a table is a database object, then a filter is a database object if your database system supports that. So yeah, this directory maintains the database, the metadata about different database objects. And like, for example, if you're doing a sequential scan, assume that you have a table and you have started inserting rows into that table and you don't maintain an index. Uh, for example, like forget for a moment that you don't have index and your database system doesn't support indexes and you're doing a sequential scan. So what you'll do first is when you run that select from that table name, your database system will look into metadata and then it will figure out where that table name is, and then it will have a corresponding starting page number, and a file name. So you'll jump to that file and you'll get the very first page. And from that, you can just go on traversing and just read the database file out till you reach the end of it. And yeah, so that is pretty much it. So SQLite, what SQLite does is it stores all of your database in a single file. So it has a header and it has a metadata section, and the metadata section is itself a table. So you have to first read out that metadata table, and when you're reading that table, you need to scan through that what tables and indexes are listed there. Then when you find the table you need, there's a column named the first starting page, I guess, and then you read that page, I mean the page number, and you just jump in that database file to that page number. So as I've said, that SQLite just uses one file for the whole database. So even if you have multiple databases, it will be stored in that one file. Even if you have multiple tables, multiple indexes, it will just be one file. So SQLite is a good system, and I think its Rust rewrite is coming through by the name of TersoDB. I have not jumped into that though. Also, SQLite is a single writer, so you can have multiple readers, but when you do a write operations, it can be a bottleneck because it has one writer. But then also, that moves out the need of concurrency control and locks, and you still need reader and writer locks for those like multiple readers and one writer, but it removes the overhead of having multiple writers writing to the same file and to the same structures. Like if you have a B tree, you define a table, and by default you get a tree organized storage. Sorry. And by default you get a tree organized storage in a form of a B tree. And when you are doing a write, so assume that you have multiple writers, you need to have some ordering, you need to hold some locks, uh, latches in database terms that those are called, but they are locks. So you need to hold some locks to prevent those writers from corrupting the B tree. But in SQLite, you just have one writer, so there's no need for that. But in TersoDB, that is you can have multiple writers there. You can have multiple readers, but you can also have multiple writers. So that would be interesting. Although I still am skeptical that TurboDB will be able to wipe out SQLite or not. I'm not very sure though, because SQLite is so embedded into systems. Even like my phone runs it. If uh, airplanes run it, airplanes use SQLite to store the data locally. Anyways, is enough of that. So let's talk about page headers now. We talked about how pages are organized on the files. Let's talk about what pages contain, what data is contained in them, how they are internally looking, how do they look like internally, and yeah. So we talked about how it is organized. So here is a database file. Assume this is a database file. Okay, assume this is a database file. There are multiple pages in the database file. But we have not discussed yet what these pages are. So now we'll start discussing what these pages are in a single page. So every page has a header. So what is contained in the header? There could be page size usually, but page sizes are predefined that you look up somewhere else to read that page, that how much bytes I want to read. But the page might also contain the page size. Then you have checksums for the data that when you're inserting data, you calculate a checksum to ensure that the data is corrupted or not. Then you store the database version, that what database wrote this, because when you're doing upgrades, then you might need to push some update that needs to know that what kind of data I'm dealing with. Because if I'm running Postgres, let's say 15, and I'm directly jumping to Postgres 18, and in the middle of that, if the developers have changed that how some data is being written, then Postgres needs to know that what original version wrote this data out, because a lot might have had happened in those two version changes. Then you have some data about transaction visibility. That's if some of you know, that's transaction max and transaction min, those two variables. Those are just multi-version concurrency control of Postgres. Uh, uh, yeah, so if you're familiar with Postgres, it uses MVCC, which has it maintains timestamps for transactions and tuples. So it whenever you are running two transactions, and you're touching the same tuple, it will copy that tuple into two different versions, and it will maintain timestamps that what transaction should be able to see that tuple. So we'll get to that. It's a long course, and we are just in the first part of the slides. Then compression and encoding metadata, that your page might be compressed and what algorithm you have used, what kind of encoding you are using. So in order to decompress it and to read it back, you might need to store that data in the header. Then you might have schema information. We talked about self-contained pages, that some database systems use self-contained pages, that all the information you need to read, all the information you need to read the page is in the page itself, that you don't need some metadata to tell you that these are my columns and these attributes are null, or like these attributes correspond to this column name. So that information might be contained in the header. Then you might have data summary and sketches. What that means is some database system might store that what key ranges you are storing. So let's say I'm doing a range scan. Uh, I'm doing a usual range scan and I'm reading all the pages. So if I store in the header that I'm storing minimum this key, a range from this key to that key. So that is my minimum and that is my maximum. And if my search point is not lying in that range, then I'll just skip those. That could be a useful information rather than reading the whole page out and then decompressing the data and then iterating through all the tuples and then picking them out, which might be wasteful if I have uh, no results come out of it. If my resultant set is null, then there's no point of doing so much work. So that might be a good information that you're storing data summary there. Sorry about that. Okay, so Yes. So that last line reads that some system require pages to be self-contained. That is also for disaster recovery. That if you lose metadata, then you can still read your pages. So uh, let's talk about page layout. So page layout. What is a page layout? That how you're storing pages. Sorry, how you're storing tuples. So we look to this. So this is my header. We're discussing right now this particular thing. So header is gone. We'll forget about it about for a while, and we're talking about how the data is stored. So storing that particular data has three types of basic approaches. You can store it as a tuple, like you have tuples, like you're inserting, you have a table, let's say you have 10 columns, and you store those 10 columns one after the other, like in a tuple format. You have something known as a log structure storage. What is a log structure storage? Um, in a log structure storage, what you do is you start writing logs. So what is a log? You just append to a log. So log is just a basic file. So whenever you have to store your data, you append to that particular file. You don't go to specific locations and edit the file, but you just append, and that is log structure storage. So tuple-oriented storage is when you are writing tuples, but when you need to edit, like when you're running updates or deletes, you're affecting that particular tuple in the page. But in log structure storage, you just append the change to the file. And when I have to read back, I need to read back the log file from the end to the start. We'll discuss about this also. There are some optimizations for that. And then you have index organized storage. What is an index organized storage? Index organized storage is when you have some index, when you are writing your data based on some index. So I'm maintaining this index, and when I run inserts, I look at that index, and that decides that how I need to insert my data into the file, into the page. So we'll discuss more about this. So let's talk about this. So yeah, Andy highlighted that in that particular lecture, they were discussing about tuple-oriented storage and how do you store tuples in the pages. And those are for the next lectures. So yes, so Andy gave like a brain teaser that how would you store it? Like even if you're watching this, hopefully no one is watching this, by the way. That would be terrifying. But if you're watching this, then I need you to pause this and think that how would you store your tuples in this? So what Andy gave the strawman idea was that you could just write in the header what number of how many tuples you have, and then you just start appending to it. So what he meant by that was that this is the header, so that's the number of tuples, and then you write first tuple out, T1, T2, T3, and then you so on, and you start filling the page. Now, so he has aligned it, but these might not be aligned. You can align them. Like if you have a tuple, let's say tuple one is this long, and tuple 2 just ends here, then you can just pad it with zeros, but that doesn't solve the problem. What basic problem do we have? This looks very familiar to something known as segmentation. Just hold on. Yes. So this looks very familiar. Okay, so what we were discussing is that there might be a cut in the video, but we were discussing that a Strawman ID would be just to append tuples to the file. So you're maintaining the number of tuples you have stored in the page, and then you start just appending wherever you find a place. But there are a couple of problems with this. Now, when you start deleting tuples, this is the same problem that comes up in segmentation in operating systems, that when you start deleting things, then you end up fragmenting your memory. So what happens is that if you delete tuples 2 and 4, Now you end up fragmenting your page. So you might compact things like this, like you might have to do extra work to compact the page and move all the memory to one place. But there's also a problem that what happens when you do a variable length attribute tuple? What happens when you don't maintain this alignment? Then you start inserting randomly into this. And then when you delete, then it would be harder for you to claim that space back. So you might end up fragmenting your page, and on a large scale, this might end up being a bad idea. So, uh, so also with this, whenever you move a tuple, you need to update all your indexes those are pointing to that tuple. So let's say I deleted tuple 2 and 4, and just assume that 4 is deleted, and I compact this page. So what I did in compaction, it's not actually compaction, but let's say I I garbage collected my dead space. So when I did that garbage collection, I moved my tuple 3 to up, like with tuple 1. So what I did, I moved my tuple 3. But now the problem is that I moved my tuple 3, but some indexes, assume I have 100 indexes on this table. I need to go and update all those 100 indexes that this is my new location. That also depends where your indexes are pointing to. They might be pointing to the primary index, which might be pointing to this. Then you just need to update the primary index. But over and all, you just need to do some extra work for this. So this is a bad idea, and a better approach is something known as a slotted pages. So what you do in slotted pages is is very simple. It's very simple. You maintain a header we talked about, and after the header, you maintain a slot array. What is a slot array? Slot array is nothing but it's a pointer to the tuples. Now I'll show that how it fixes the problems. So what you do, you maintain a slot array and you start appending tuples from the end of the page. And you just maintain pointers in the slot array to those particular tuples. So what it ends up doing is that assume you have some index, let's say this is a B tree, you have some index and your keys are pointing. So now your keys won't point to the physical location of the tuple. I mean, they would, but they would point to this, the slot array, that this particular thing, you need to go and read this slot array. So what happens is, whatever I do inside this page, I can just update this slot array. So assume that I move tuple 1, I move it from here to some random location here, tuple 1. I don't need to go and update this particular B tree. What I need to do instead, I just need to update this particular one pointer to point to the new location in the page. And all my indexes above, they still know that I just need to read the offset one. I mean, I just need to read the slot one of that slot array. But inside my page, I can do anything now. I can just move tuples around and I can compact space without, I just don't have to tell the outside world that I'm moving things around in this page. Because for outside world, it is still that if I read the slot array at point 0, then I will reach my tuple. So inside the page, I can do anything. So this moves like even if I have fixed and variable length data, you can still manage this. That if you have deletions and then you have insertions and then you run a vacuum, vacuum is garbage collection in terms of Postgres. And when you run vacuum and you clean up your pages, then even if you're moving tuples around, you don't need to tell the outside world for that. You just have your indexes pointing to the slot in the slot array, and your slot is pointing to the internal location. And when I'm bringing this page into memory, so think about this also. When I'm doing this compaction and like when I'm doing this vacuum and when I'm updating this page, I have this page in memory. I have this whole page in memory, and doing this reordering in the main memory is quick. Doing it on disk would be hard, but I have this page in memory. So being in memory, it's a cache, sort of, for my database system, and it is fast. So moving this and moving tuples around and doing this pointer swap is quick for me. So I just this is one of the best ideas that I've that struck me while I was watching his lectures. So yeah, and when you say uh, you start moving, like you do more slots and then you start appending, and at some point these two lists will meet each other, like the number of tuples and the slot array will just start will reach a point where there's no more space in between. There might be some wasted space that you cannot put any tuple in, but when you reach certain point, then you can declare that this page is full. There still might be certain space, but still it's not as wasteful as this strawman idea of just appending things to the page. And yeah, so yeah, so this in this slide, they are see that the first thing is pointing that, and we have a slot. The second slot is pointing to tuple two. Third slot is pointing to tuple three, and fourth is pointing to the tuple four. And as I was talking, that you grow the slot array from beginning to the end, and you grow your tuples from the end to the beginning, and at some point they will meet. So yes, so assume that you delete tuple three. So in this slide, it is being shown that tuple three is being deleted. So my tuple 4 is there. Now all I can do is just slide tuple 4. Look, my fourth slot was pointing to tuple 1, tuple 4, and it was at some offset in the page. Let's say it was at 300th byte. Okay, sorry, 3000th byte. Assuming my 4 page is 4 kilobyte. Okay, and when I move this tuple, let's say my new offset becomes 4000. I don't want to tell the outside world, all my indexes or any filters that might be using this location, that I changed something in the page. They are still pointing to this particular offset in the slot array. So they just need to maintain that, and internally the page can be moved around, the page data. Okay, so um, just give me a moment. Have water. Okay. Anyways, so let's talk about record IDs. What is a record ID now? Record ID is a physical location that the database system assigns to your tuple. So for every logical tuple, the database system will assign a record ID which will define its physical location in the database file. So we talked about page locations, that you need a file name, a page number, and a page size. Then you can just offset into the database file. But how do you jump to a tuple in those pages? So you jump to it by a record ID, a record identifier. What that does is it will give you that I need to go to this page number and this particular slot in the slot array, and that will be my identifier for the tuple. So assume that you have a B tree, and my B tree is pointing to physical locations of the tuples. So what data will be stored? So let's say for key K1, what value will be stored? It will be this record identifier. It might be it might be a file name it might be a file name along with page offset along with the slot offset, or if you have the file name already, it might be just the page number and the slot offset in that page. So for example, a file ID, page ID, and slot number. And SQLite uses row ID as the root primary keys and store them as hidden attribute. So what this line means is that no matter what primary key you give to SQLite, it will already create a B tree, like it stores your data as a B tree, as a tree organized storage. So it will generate a synthetic ID for you for each tuple, which will be hidden from you. So you might define your own logical primary keys, but SQLite will maintain its own record IDs for your data, and it will maintain that primary key index, and your primary key will just be a secondary index for that. So no matter what primary key you give to SQLite, it will just use its own primary key for that, and your primary key would just be a secondary index pointing to that primary key index. So in this slide, it's shown that Ingress used 4 bytes of page identifiers. Ingress is the precursor to Postgres, and uh, so Postgres uses 6 bytes, and we have different for different. We saw CTIDs in the last tutorial. So it was giving me a page offset, sorry, page number, and the second part was the page offset. That what slot do I need to read? And there were a lot of slots. Like when I inserted 300 tuples into the page, uh, page 0 was storing 112 tuples, I think. So there were 112 slots in that slot array. Okay, so there is a very important line that application should never rely on these IDs to mean anything. So usually it is applications are designed this way that you just depend on the logical primary key that you are defining and logical keys that you know about and not these physical locations. So like nobody is doing that select star comma CTID from this particular table and storing that CTID somewhere and then expecting that when I do look up on that CTID again, then it might be there. If you're doing it wrong. You shouldn't read that CTID. So it is that was for demonstration purposes. But when you're delivering production systems, you shouldn't be dependent on CTID and physical location identifiers because the database system, as we discussed, that the page might move, data might move, so the data in the page might move. So you shouldn't be dependent on what physical location it is currently because it might not be there when I run vacuum or my data, like my statistics decide that it's time to compact things up. So, okay. So tuple layout, we discussed about this. No, we discussed about page layout. So we looked at file storage, what kind of pages storage, like this is a file, page storage, that what ordering my pages have, how do I store pages. Then I looked at page layouts, that within this page, how do I how do I go about layouting my whole page so that I can efficiently store tuples into it. Now what we'll look at is tuple layout. What is a tuple layout? You are now jumping to the granularity of things. Now you're inside the tuple, you're inside the page. Sorry, imagine like this. You're inside the database file. Now you're inside a particular page, and now you're inside a particular tuple. Now I'm standing at a tuple. I want to see that what optimizations can I do to the tuple so that I can just store it very efficiently. So this is what I'm talking about, tuple, right? So what I'll show you. This is DB file, DB file. Let me not draw it here though. This is my file. This is my particular page, and these are my tuples. Ignoring that we have slot, like forget about slot arrays for a moment, and we have tuples inside this. Small tuples. So this is my file, and this is my page, and these are my tuples. Now what we are looking at, we are going to start how these tuples are organized. So tuples. Okay, so I'm just clarifying that what we are going to start, and I have to rush somewhere, so we'll start this in the next video.